Hi friends, welcome to my channel. In this video, we are going to see about the emerging materials for future devices. They are graphene, carbon nanotubes, zinc oxide and silicon carbide. About the properties of graphene. Graphene is a two-dimensional crystal of carbon atoms arranged in a hexagonal or honeycomb lattice. It is harder than diamond and has high tensile strength. It is 200 times than silicon. It has light. It is 5 times stronger than steel. Next is the methods of producing graphene. There are two main methods of producing graphene: exfoliation and epitaxy or chemical vapor deposition. In exfoliation, they produce flakes of varying size in powder form, and this graphene is known as natural graphene. There is also liquid phase exfoliation, in which graphite is suspended in liquid and then exposed to high frequencies of sound to produce graphene flakes. The graphene produced by this method are used in polymer, paint and lubricant production. The next method is epitaxy or chemical vapor deposition. In this method, substrates such as silicon carbide, nickel, copper or iridium is heat treated in a gaseous atmosphere to produce a film of graphene. Graphene produced by this method is considered as synthetic graphene and it is free of impurities. It is expensive and used in various electronic applications and also in clothing. Next is carbon nanotube is a tubular form of carbon with the diameter as small as 1 nanometer. It has long hollow structure with the walls made of graphene. It is strong, flexible and stiff. They have high current carrying capacity. Next is properties of carbon nanotubes. Carbon nanotubes have a high tensile strength due to the sp2 bonds between the individual carbon atoms. They are very elastic, that is stretchable. They have high thermality, that is it conducts electricity very well. They are highly flexible, that is it can be bent without any damage. They have low thermal expansion coefficient. These carbon nanotubes can be classified as single-walled carbon nanotube and multi-walled carbon nanotube. Single-walled carbon nanotube has a single layer of graphene in the form of tube or cylinder. Multi-walled carbon nanotube has multiple layers of graphene in the form of. Next is production of carbon nanotubes. They can be produced by three methods: arc discharge method, laser ablation method, chemical vapor deposition. In arc discharge method, two graphite rods, one is anode and other is cathode, are placed in an inert environment, that is in helium or argon, and a strong current of 100 amps, either DC or AC, is passed between the two terminals, that is anode and cathode. This generates arc-induced plasma that evaporates the carbon atoms in the graphite. Nanotubes grow from the surface of these terminals. Next is the laser ablation method. Third, graphite is placed in a long quartz tube in a furnace controlled at high pressure and temperature. Then laser beam is focused on the graphite and this evaporates the carbon atoms in the graphite. Nanotubes mixed with the undesired amorphous carbon collected on a cooled substrate at the end of the chamber. Both of these methods can produce only a limited quantity of carbon nanotubes, but chemical vapor deposition method produce bulk amounts of carbon nanotubes at relatively low temperature. In this method, substrates such as nickel, cobalt, iron is heat treated in the gaseous to initiate the growth of carbon nanotubes for application in cancer treatment, platelet activation, tissue generation, energy storage and drug delivery. Next is zinc oxide. Zinc oxide is an attractive material for applications in electronics, photonics, acoustics and sensing. It is a direct band gap semiconductor which has band gap of 3.4 electron volt and high refractive index 2.008. It has high exciton binding energy 60 milli electron volt, because of which it finds application in optical devices. It has high optical transmittivity and high conductivity. Electromechanical coupling in zinc oxide is very large. Production cost of zinc oxide is relatively low when compared to gallium nitrate. It is a stable light as compared to gallium nitrate. Next is heterojunction of zinc oxide. Preparing homojunction of zinc oxide is difficult because p-type zinc oxide preparation is challenging due to low reproducibility, instability, low conductivity and limited carrier concentration. Hence, heterojunctions of zinc oxide are realized using various p-type materials such as silicon, silicon carbide, gallium nitrate, gallium arsenide, aluminum gallium nitrate, etc. These function in optical devices such as LEDs, photodetectors, solar cells and optically pumped lasers, in acoustic wave devices and also in biosensors and gas sensors. Next is silicon carbide. Silicon carbide is also known as carborundum. It is a semiconductor which have equal amount of silicon and carbon in a hexagonal crystal structure. It is one of the rarest materials in the earth, but it is abundantly available in space. Its breakdown strength is 10 times higher than that of silicon. Breakdown strength is nothing but ability to withstand the high voltage. A variety of polytypes of silicon carbide exist, like 2H silicon carbide, 4H silicon carbide, 6H silicon carbide. Polytype is nothing but different crystal structure of the same chemical compound that are identical in 2 dimensions and differ in the 3rd dimension. Here H represents the hexagonal structure. Of these polytypes, 4H silicon carbide is the most ideal for power devices. It has a wide band gap of 3.2 electron volt. That is for 4H silicon carbide. Now we will see about the properties of silicon carbide. It has high thermal stability to withstand heat. It has external chemical stability and high thermal conductivity and low electron and hole mobility when compared to silicon. It has high breakdown strength, that is the ability to withstand high voltages. Silicon carbide finds applications in solar power inverters and other power supplies, also in wind turbines, military systems and sensor systems. Next is the comparison of the 4 materials. If you see graphene, an undoped graphene has zero band gap. So because of zero band gap, it has high electron mobility of 2 lakh centimeter square per volt second and hole mobility greater than 1 lakh. Carbon nanotubes, single walled carbon nanotubes, have band gap of approximately 0.008 and it has electron mobility of 1 lakh centimeter square per volt second and hole mobility of 20,000 square per volt second. If you see zinc oxide, it has a band gap of 3.4 electron volt, electron mobility of 200 centimeter square per volt second and hole mobility 180 centimeter square per volt second. And silicon carbide, the most widely used is 4-hit silicon carbide, has electron volt of 3.2 and electron mobility of 900 centimeter square per volt second and hole mobility 100 centimeter square per volt second. Of these four materials, graphene and carbon nanotubes have high electron and hole mobility, hence its conductivity is high. But when you see zinc oxide and silicon carbide, it has low electron and hole mobility, hence its conductivity is less. Thanks for watching the video. For more videos, subscribe to our channel.